In this video, I'm going to introduce you to the process of anti-differentiation. So, anti-differentiation is basically the opposite process of finding a derivative, and they're often referred to as antiderivatives, which you see here. So, we've already learned how to take a function, go through the process of differentiation, and find what we've called its derivative. Well, in this particular type of process, we want to start with a function, but we want to work our way backwards and find the original function that would give us a particular derivative, and that's called anti-differentiation. Now, traditionally, if you are competent with your derivatives, anti-differentiation is not going to be an issue. It's just a matter of kind of getting our brain to work in the opposite direction. So for example, if I take this function x squared over 2 and I find its derivative, so the derivative would say multiply by the exponent, so 2, just going to show it up here, 2 multiplied by x squared over 2. Oh, I got to take one off my exponent, sorry. So 2x to the 1. Well, the 2's would just cancel, and it actually turns out to just be x. So that's the derivative. Well, the antiderivative of x, right, so this is the derivative. The antiderivative would be if I started at x and said, what function would I take the derivative of that would give me this as its derivative? Well, that would be x squared over 2. That's called the antiderivative. Derivative. Now, one thing that's a little different with antiderivatives, though, is if I had started with x squared over 2 plus 2, and I did its derivative, would I not end up also with the same thing? Because I'd take the derivative of my function, which is the same as this, which is going to give me x, but then I've got a constant, and we know that the derivative of a constant is always 0. So in theory, if I had f of x equaled x squared over 2 plus 7 plus 8 plus pi, take away 10, if there's any constant tacked on the end here, you'll get that same antiderivative. So when you're doing antiderivatives, we get what's called a general antiderivative. And what we do is we just put a plus c at the end to indicate that there could be some constant tacked onto the end. And it says here that c is just some arbitrary constant. You'll see how that comes into play here as we kind of do a few of these. So here's an example, knowing what we know about functions. If you had some function, let's say x cubed over 3, and then I had plus 3, plus 2, plus 1, minus 2, these are all just the same function with a different vertical translation. If I was to just take, let's say, this point right here, and draw tangents to the curve at the same x value, well, just with those quick hand-drawn sketches, I think you would agree that pretty close to having all the same slope, which indicates that whole notion of derivatives, which is slope of a tangent. So even though they have a different vertical translation, right, different number out here at the end, I still get the same derivative at a particular, so I pick this x value, whatever it is, and when I went up and did my tangent line at each one, I got the same thing. So f prime was equal at all of these different locations, as long as the x value was the same. And that reinforces what I just told you. It doesn't matter about this number out at the end. Your derivative will still be the same thing. So that's what I'm just saying here, but my tangents all have the same slope. Okay, so let's take, oh, I must have missed a slide here. I did, sorry. So a couple of rules we want to uncover. The first one is, how do we get the antiderivative of a number? So think in your head if some function was 3. So now we've got to think backwards. Ask yourself, what function did I take the derivative of that gave me an answer of 3? Well, thinking of the rules that we know for differentiation, if I had, now Sometimes students say, well, isn't this the derivative? No, it's just some function. But make sure you don't call the antiderivative the same thing as the original. So kind of a common notation you'll see is if this is lowercase, just call its antiderivative capital F of x. Well, how about if I had 3x and said, well, take the derivative of 3x? Well, it's just 3. But you got to remember that there could have been some other number at the end of it, because if I had 3x plus 7 and took the derivative, I'd still get 3, because the derivative of your constant is going to be 0. If my function, to start out with, f of x was negative 4, well, the function I must have taken the antiderivative of, the derivative of that gave me that answer, must have been negative 4x plus some constant c. So that leads us to our first basic rule of antidifferentiation, and it is simply that, get rid of this, if you have any constant, I'm just calling it k, the antiderivative of a constant is that constant multiplied by x plus some general constant c. So that becomes very easy. If f of x is 12, the antiderivative of the number 12 is 12x plus a constant. Meaning if I took the derivative of 12x plus a constant, I would get that result. So the next thing, so that's our first rule of antidifferentiation. The next thing we want to be able to do is undo the power rule. And again, you're going to put your brain in reverse. So I've got a function here that I took the derivative of, and I got 6x squared as my derivative. So my question is, well, what function must that have been? Well, here's the first thing we know. We know for sure, so this is f prime, the original function must have been a 3. Because we know that the power rule says you multiply by the exponent and then you take one off. So if my derivative has an x squared, I must have originally had an x cubed. So add 1 to the exponent. Now, to get the number in front, you say, well, how would I get a 6 here? Well, to get a 6 there, this must have been a 2. This is my f of x. Well, let's think about, let's do a power rule just to refresh your memory. If I had 4x to the 5th and I did the derivative, I multiply these two together, and then I take one off the exponent. So we're basically trying to reverse those steps. So the last thing I did is I took one off the exponent. So to undo that, I add 1 to the exponent. Now, here I got a 20. The way I got the 20 was by multiplying these two together. So what do you think you would do to undo multiplying two numbers together? Well, you would divide them. So what we have now, we have to divide by, in order for me to get back to the 4, I'd have to take this number 20 and divide by that original exponent. So to undo the power rule, we add 1 to the exponent, and then number 2, you divide by the new exponent, meaning after you add 1. And that's kind of our rule summarized. So add 1 to the exponent and then divide by the new exponent. So if I look at this one, let's see if that works. Add 1 to the exponent, 3. Divide your coefficient, in this case 6, by the new exponent. 6 divided by 3 is 2. And then of course remember there could always be a constant stuck out here at the end. Okay, if I try and put that into a nice formal rule then, with notation, here is a way to undo power rules. So if you get some constant and then x multiplied to the power of n, to undo that, we are going to add 1 to the exponent. Right? It was n, now it's n plus 1. We're going to take our original coefficient and we're going to divide by the new exponent. Here it is in words down here. Add 1 to the exponent and divide by this new exponent. That is how we anti-differentiate power rules. Okay, so let's try a couple. Just do a couple here on their own first, and then we'll get into some more complicated ones. So if I had this function, f of x was 7x to the fourth, and I wanted to find the antiderivative. Capital F of x, I add 1 to the exponent, so it's going to be 5, and I divide my coefficient by the new exponent. 7/5 x to the fifth, and of course there could always have been some constant there in the beginning. Now if you doubt yourself, check it. Let's do the power rule on this and see if we get this back as our derivative. 5 multiplied by 7 over 5 would give me 7. Take 1 off my exponent would give me that. So it's got to be right, and the derivative of a constant would be 0. I don't know. And these can be fraction exponents, ugly exponents. Let's say I had 3x to the 2/5. Now, add 1 to your exponent. Now, when you're adding 1 to your exponent, in your head, think, just if you have fractions, 1 in this case would be 5 over 5. So I add 1 to 2/5. That's going to give me 7/5. And let me just jot that down here. There's 1 added to my exponent. I take 3 and I divide by my new exponent. Well, if your new exponent is a fraction and you're going to divide by it, you multiply by the reciprocal. So this is going to become, my antiderivative would be, so my new exponent is 7/5. I'm going to divide by 7/5, which means multiply by 5/7. That's going to give me 15 over 7 x to the 7/5 plus c. Okay, so let's put a bunch of these together now into just some polynomials, or not even polynomials, just expressions, I guess. And let's see if we can anti-differentiate this. Okay. This one, the only term this one's fine. You always want to have a number, x to an exponent. A number, x to an exponent. Number, x to an exponent. This one, I think I'll just make sure I envision that it's really 2x to the -2. That one's fine. There's a constant. So here goes our antiderivative of this one. Add 1 to your exponent. It's going to be 6. Divide by the new exponent. 1/6 x to the 6th. Minus. Add 1 to your exponent. It's going to be 5. Divide by your new exponent. So 2/5 x to the 5th. Subtract 3/4 x to the 4th. Where are we at? 2x to the -2. So add 1 to your exponent. You'll get -1. Divide by your new exponent. So it's going to become -2x to the -1. Add 1 to this. You're going to get -2. So it's going to be -5 over 2 x to the -2. Antiderivative of a constant is 5x, and then remember there could always have been some number out here at the end. And there we have it. So if I took the derivative of this, I would get back that original function. Alright, so I'm going to put up one more here. Oh, I skipped it, sorry. And we are going to, let me see, did I have another underneath this one? Oh, sorry, let's look at this one. I don't want to get into the trig ones yet. Okay, so let's undo this one. So it's a little messy looking here. For now, so this is one I think I definitely rewrite first. So let's go f of x is equal to, so instead of 3 radical x, that's 3x to the 1/2. Take away, now you get 2/5. But instead of x to the 4th in the denominator, we jump that up to the numerator and make it x to the -4. I'd have x to the exponent 7/5. Let's see what we've got here now. So I've got minus 6. Now let's do a little side work here. So this is x to the half. The denominator is x squared. So I need to subtract those exponents. 1/2. Take away 2, which would be 4 over 2. This is really then x to the negative 3/2 plus e squared. Now e is just a number, so this is just a constant. Okay, so let's undo these power rules. Add 1 to a half. So you add 2 over 2, you're going to get 3 over 2. To divide by 3 over 2, you're going to multiply by 2/3. So 3 times 2/3, the 3's will cancel. You're going to get 2x to the 3/2. Add 1 to my exponent in my next term is going to be negative 3. So divide by negative 3, that's the same as multiplying by a negative 1/3. So that'll make this 2/15 x to the negative 3. Add 1 to my exponent, 7/5. So add 5 over 5, we're going to be at 12 over 5. Dividing by 12/5 is the same again as multiplying by the reciprocal, so this will be 5/12 x to the 12/5. Add 1 to negative 3/2, so add 2 over 2, that's 1. That's going to give me negative 1/2, which means I'm going to multiply by the reciprocal, which would be a negative 2. That'll make this a plus 12 x to the negative 1/2. Remember, this is just a constant. It's just trying to fool you because of that exponent, but it's still just a number. The antiderivative of a number is that number times x, and then, of course, you could have some constant out here, plus c. And that is anti-differentiation. So what I've shown you in this video is how to anti-differentiate basically a constant and how to undo power rules. In our videos to follow, we'll look at how to anti-differentiate many of our other patterns of derivatives that we've already studied, trig functions, chain rules, etc., etc. All right, so there'll be some practice questions on these that you can use to ensure you understand. If you have any questions, just reach out and I'll see if I can help you out. Thanks for watching.